All right, so we're looking at linear combinations of vectors. The motivation comes from looking at solutions of linear systems. You can see that what you're doing when you solve a linear system can be thought of as finding the right linear combination of the column vectors to equal some other vector. So we're going to start looking at the geometry behind this. Span of a set of vectors we've got defined here. Okay. Come on.
Quick question. Can you remind me what the difference is between, well, I know the double line means vector, the single line, single underline, the A1, A2.
The underline means it's a vector.
Oh, okay.
Okay, so sometimes I use an arrow on top, sometimes an underline, but right, we've got right here, it's a set of vectors.
Got it.
Come on, set of vectors. So we use double underline to tell us we're talking about a matrix. One underline, we're talking about a vector. All right, so anything that you can get by taking a linear combination of vectors, right? So x1, x2, xk are whatever scalars you want. The set of everything you can build like that is the span of your set of vectors. So a vector B is in the span if and only if you can find these x's such that you can build the vector B as a linear combination of the vectors in your set. Okay, so clearly this is exactly what we started talking about. This is exactly what the motivation was. This is exactly the structure that we observed when solving linear systems. Okay, and I before we go on, does everyone have what they need off this page?
Hold on, can you wait just one more second so I can get the last sentence?
Okay, sure. Okay, does anyone need
Scroll
more
the page down a bit?
So I can't scroll anything. You should be able to do that on your side.
I can't.
Okay, so how far down can you see? Can you see to here?
Yeah, I can't see past such that.
Past what I just drew?
No, I can see if and only if you can find xk such that, and then it stops.
Okay, can anyone see the last line of this page? All right, so let me just go to the next page then. Okay, that was the last line.
Thank you.
Okay, you're welcome. So let's think about the geometry of what's going on. If you think back to Calc 3, Math 243, what have I got here? So
A line.
it's a line. Now the notation for vectors is it's different in calculus, but the idea is exactly the same, right? We can think of a line as the set of vectors of a certain type, and notice what you have here. You've got one base vector, right? Gets you onto your line. And then you're taking arbitrary linear combinations of another vector, arbitrary multiples of this direction vector v that move you along your line. Okay, so you've got a certain set of linear combinations there. And what's the span of one vector? That's the set of all multiples of the vector. All scalar multiples, right? So that's the set of vectors of the form t times a1 such that t is a real number. Okay, so the span of one vector essentially you can think of as representing a line. What do you think the span of two vectors might represent?
A plane.
Exactly right. So, oh, sorry. Did everyone have what they need off this page?
No, 1 second.
Okay.
All right, I'm okay.
Good. Thank you. Oops. The span of the set A1, A2 identified with a plane. Okay, and so on. And if your vectors are higher dimensional or you're working in a higher dimensional space, it becomes difficult to visualize, but sometimes we talk about hyperplanes in this context. Okay, so there's a connection with geometry there. And there's a result. To think about here. So suppose you've got your set S, you've got vectors A1 through AK. And we're going to set, we're going to make a matrix So the notation here, hopefully it's not confusing. A is matrix with A sub i's as its columns. Okay, so S is the set of the vectors. We build a matrix using those vectors as the columns. And the vector B is in the span of that set if and only if our linear system AX is equal to B is consistent. All right, so remember, consistent means what?
It has at least one solution.
Exactly, very good. Okay, so so really this is just a restatement of what we've already observed earlier. Just it's just expressed in slightly different language. Okay, so does everyone have what they need off of this page? Everyone good? No? Okay. All right, does anyone need more time? Okay, everyone's good, I hope. So let's just, oh, let's do an example here. So we're going to start with a little one. Okay, so we've got these two vectors, A1, A2, we've got a vector B. Come on. Is that vector B in the span of the set made from the vectors A1 and A2? Well, how could we answer this question? We can actually set up this linear system. Actually, let me call this X1 and X2. Right, so, and how can we tell whether the system is solvable? It's pretty easy to tackle directly, but what if we had vectors that had 40 entries each, and this was a really large system? How could you tell whether it was solvable?
Do we put it in RE form?
Exactly. Good, good, good. Okay, so we're going to go to the reduced row echelon form. Let's just look at our augmented matrix. And I like that first row. I've got my pivot. I want a 0 below the 1 in the upper left. I can get that by replacing row 2 by row 2 minus twice row 1. So I get a 0 here. 1 minus 2 becomes -1. 2 minus 2 times -1 becomes 4, I believe. And I can make a pivot now on the bottom right. So I multiplied my second row through by -1. And now I can get a 0 above my pivot in the lower right corner by replacing row 1 by row 1 minus row 2. That becomes a 3. And we noticed that we were able to get to the identity on the left, so our system is solvable. In fact, this solution is unique. We don't have any free variables. So in fact, right, the solution of this linear system tells us exactly which particular linear combination of the column vectors we need to take, right? X1 is going to be 3, X2 is going to be -4. That combination, 3 times A1 minus 4 times A2, will give us the vector B. Oops. Okay, so this is just a slightly different point of view of what we're doing when we solve a linear system. Okay. So does everyone have what they need off of this page? Everyone good? Okay, so we need some more terminology. So we're going to define what's called a spanning set. Does this keep going? All right. So we have what's called a spanning set. So S again is going to be a set of vectors. Okay, there's going to be K of those. K is arbitrary. So each of the vectors in my set is in Rn. So these are column vectors with n entries. Okay, so hopefully that language is clear. So we say that this set of vectors is a spanning set for Rn, right? So by this, we mean the set of n entry column vectors. If for any vector b in n-dimensional space, which we're thinking of as column vectors, we can solve b is equal to x1 a1 all the way up to x sub k ak. Right, so in other words, any vector, any n component vector we can represent as a linear combination of the vectors in our spanning set. So another way to say this is that so this matrix A has as its columns the vectors a sub 1, a sub 2 up to a sub k. If we build that linear system, we should always be able to solve that linear system. Okay. So is this statement clear to everyone? Does anyone need more time on this page? Are we good to move on? Okay. So once we have this idea, we can add to it another useful idea. So-called linear independence of a set of vectors. And here's the motivation for worrying about linear independence. So let's say we've got a vector A1 that looks like this. So that's a vector in R2, right? Set of two component column vectors. And let's say A2 looks like this, and A3 looks like this. So we can think about the span of the set A1, A2, right? That's the set of everything I can get by taking a multiple of A1 plus a multiple of A2. And if the X and the Y are arbitrary, notice I can use this to build any vector in R2. Right, I can get any vector I want by taking linear combinations of those two vectors. So do we get anything more by appending another vector to that. All right, so why wasn't A3 included in the span? It wasn't included because I first wanted to look at what I could get just out of A1 and A2. Okay. So let's look at the span of those three vectors. Right, so that's the set like this. Now, notice that I'm adding up two component vectors. And just with the first two vectors, I could get any vector in R2. So do I gain anything by adding that third vector in? Well, we don't lose anything certainly, but we don't gain anything. We can still get to any vector we want. And if we had a set X, Y, Z that let us build a particular vector in R2 as part of the span using those three vectors, well, we could just replace Z by 0 and modify X and Y to build the vector with only the first two. Okay. So the point is that the span that I have from the first two vectors is the same as the span of using all three vectors. Okay, I don't gain anything by adding that third vector in there. And often in mathematics, we want to try to be as sort of as efficient as possible. So we're interested in this distinction. We're interested in, are we gaining anything by adding another vector to our set? Okay, so this is related to the idea of linear independence and linear dependence of a set of vectors. All right, so so this is the motivation. Does anyone have any questions on this argument? Does anyone need more time to copy down this page? Are we good to go? Okay, so we're going to define what we mean by linear dependence. So the set of vectors S equals A1 up to AK we say it's linearly dependent if we can take a linear combination of the vectors in our set and get to the zero vector, right? So remember, we're adding up a linear combination of vectors. So this is not the number zero, it's the zero vector. The vector all of whose entries are zeros. Oops, zero vector. And we want a non-trivial solution. So clearly we could just take x1, x2 up to xk equals 0 and have a solution. But if we can solve this equation without all of the x's being 0, we call that a non-trivial solution. And another way to think about this is that, okay, at least one of these x's is not 0. So let's say x1 is not 0. Then we could move that vector with the non-zero coefficient to the other side, divide through by the coefficient, and we would be able to write the vector a1 as a linear combination of the other a's. Okay, so in a sense, you're adding a vector to the set that doesn't give you anything extra. So if we go back to this example, notice that the vector a3 we had here was just a1 plus a2. So by adding a3 to the set, we're not able to build anything extra when we take linear combinations, because wherever an a3 appears, we could just replace the a3 by a1 plus a2, and we're back to the span of just a1 and a2. Okay, so the set of vectors is linearly dependent when either you can think of building at least one of the vectors as a linear combination of the other vectors in the set, or you could go back to this this equation, of course. So how can we check a set of vectors to see if they're linearly dependent? Well, I'll get to that. Before I write it down, does anyone need more time to copy on this page? Okay, good. So let's look at the system AX is equal to 0, where this coefficient matrix A are the vectors in the set you're trying to diagnose to see whether it's linearly dependent. So we know that the system always has the solution where our vector x is the 0 vector. If there are non-trivial solutions, then the set is linearly dependent. So LD is linearly dependent. Okay, and remember, if there are solutions, there's going to be infinitely many solutions. And effectively, what's really going on there is that when the set of vectors is linearly dependent, that means you have some combination of those vectors is equal to the 0 vector. Well, if that's true, then any multiple of that combination of vectors is also the 0 vector, right? If I took this equation and multiplied through on each side by some scalar, I'd have different coefficients on the left, but any scalar times the 0 vector is still the 0 vector, right? So that's really what's going on. Any multiple of a homogeneous solution, right, in other language, is also a homogeneous solution, right? So we're connecting back to this terminology when we talked about linear systems as being homogeneous or non-homogeneous. Okay, so we're starting to see how this geometry fits together. Okay, and so we know when the system is linearly dependent, and rather than going further down the page, let me just work over here now. So if the only solution for the system is the trivial one, then the set of vectors is linearly independent. And I might abbreviate that as Li. All right, so we have a way to check whether a set of vectors is linearly independent or linearly dependent by setting up and solving a particular homogeneous linear system. Okay, so linear dependence means that associated system has non-trivial solutions, in fact, infinitely many solutions, has free variables. Linear independence means only the trivial solution to the homogeneous version of the equation and no free variables. Okay, so are there any questions on the ideas from this page? Is this making sense? Okay, so what was the last thing I said? So if you have a set of vectors, you want to check whether it's linearly independent or dependent. You can set up this, this linear system where you use the the vectors as the columns of your matrix, your coefficient matrix A here, we're calling it. And if that homogeneous linear system, right, it's a homogeneous system because the forcing, the right-hand side is 0. If that homogeneous linear system has only x equals 0 as its solution, the set of vectors is linearly independent. There's no free variables. Every column is a pivot column in terms of what happens when you get the matrix to its RREF. And then if there are non-trivial solutions, right, so there's some solution other than the 0 vector, then your set of vectors or the columns of this matrix A are linearly dependent. There has to be a way of representing at least one of the columns as a linear combination of the other columns. Okay. Does that make sense, Catherine? So there's a lot of different ways of formulating what really is the same idea. So I'm just trying to make all of those connections. All right, so when we get to differential equations, there's a notion of linear independence and linear dependence for functions as well. Okay, and it is related to what we've talked about so far, because we're dealing with functions rather than just column vectors. It doesn't work exactly the same way. But the idea is similar. So let's say capital F is a set of functions, lowercase f1 of x, lowercase f2 of x, up to lowercase fk of x. The span of f is equal to the set of all things you can build as linear combinations of that set of functions. So now I'm using C1, C2 up to CK as my coefficients. Okay, and typically we want to specify the domain on which we're working. So we could, for instance, say that we're going to work on the open set for x between A and B. Okay, so certainly we can build linear combinations of functions. And the idea of linear independence and dependence is exactly the same as we had for the columns, right? So we say the set is linearly dependent if when we take a linear combination of these functions, we can make that linear combination be identically zero. And I'm going to indicate identically zero, meaning evaluates to zero at every point on the interval from A to B, right? The symbol with 3 horizontal dashes just means identically equal to. Right, so linear combination of the functions evaluates to zero everywhere, right? That's all the equation is saying. So that's exactly the same idea. If the set isn't linearly dependent, it is linearly independent, right? So the sort of tricky part is, how do you actually check this? May not be very straightforward to try to work with this equation. Okay, may be very difficult, in fact, to work with this equation. So what could you do? All right, I need more space, so I'm going to have to move on. So does everyone have what they need off of this page? Are we good? Okay, so so let's actually copy this basic equation over. And I'm not going to bother writing the identically equal symbol. I'll just use the equal symbol. So that's one equation. If we could somehow get to a linear system so that we could use what we saw before, maybe we'd have a better idea of being able to handle this. So the question is, are there related equations that we can build if we know this is true? And the answer is yes. So if this thing on the left evaluates to zero everywhere, it's a function of x here, well, let's take the derivative. The derivative of a constant is zero. So on the left, we're just going to differentiate term by term. And in the same way, we can keep going until we have enough of these equations to actually have a linear system we can work with. So I'm using this notation here. F sub k minus 1 of x means k minus first derivative of f. So essentially, notice we start with just the functions. We can think of that as the zero derivative. Second line is the first derivative, all the way down to the k minus first derivative. So there's really k such equations. Okay. We've got these constants C1, C2 up to CK. All right, so the coefficient matrix here now, if we lump all of these together, it is going to be built out of my functions and their derivatives. So the top row of this matrix is just made out of the functions f1, f2, up to fk. If I differentiate that top row, I get the second row. If I differentiate the second row, I get the third row, and so on. One derivative each time to get the next row. And that special coefficient matrix is called the Wronskian matrix. Or the Wronskian. Okay, and we know that our set of functions is going to be linearly dependent if there's a non-trivial solution of the system. It's linearly independent if there's only the trivial solution for the system. And that, again, is on the interval where x, say, is between a and b, right? Set of functions, we have to worry about the domain on which they're defined. So if we can find the reduced row echelon form for the matrix, from that we can diagnose whether the system tells you that the set of functions is linearly independent or linearly dependent. Okay, that's the idea. So I want to write something down, but I don't have any room, so I'm going to have to go to another page. Does anyone need more space here? Sorry, more time to copy down. Is everyone ready to go to the next page? All right. Okay, so that set of functions is going to be linearly independent when the reduced row echelon form of the coefficient matrix and that is a function of x, right? Because the f's depend on x. Identity matrix. So if everywhere on the domain where we're working with the functions, we can get the RREF to the identity, our set of functions is linearly independent. Otherwise, meaning that RREF for W of X is not always the identity. Then the set of functions is linearly dependent. Okay, so this is a little bit hard to think about perhaps. So let's actually do an example. Okay. So is everyone ready to do an example? Good, okay. So let's look at our set of functions and let them be 1x and x squared. And let's just work on minus infinity to infinity. We're not really going to worry about the domain. So our Wronskian is going to look like this. We use our functions to build the first row. We get the next row by differentiating, in this case, with respect to x. And then we get the next row by differentiating with respect to x again. And we stop when we have the same number of rows and columns. Okay, so when we have a square matrix. So let's think about this. We're good in the first row, first column. We've got a pivot. We've got the 1 there. Second row, second column. We've got a pivot. Third row, third column, right? That 2 we can just divide the third row through by 2. We've got a pivot. All right, so we can get the zeros in our pivot columns pretty easily. So 0, 0, 1, I like 0, 1, 2x. I'm going to leave for now. I can replace the first row by first row minus x times the second row. Right, so second row, I multiply by x. The entries are 0, x, 2x squared. I subtract that from the first row. X minus x goes to 0. X squared minus 2x squared goes to negative x squared. And then I can do the same thing in the third column. And it's clear that, in fact, I can get rid of all the entries I want to go to 0. So the RREF, the reduced row echelon form of F, is the 3 by 3 identity. So just to emphasize that it's the 3 by 3, I'll give it a subscript 3. So what is that telling us? Oh, okay. So Noah, what was the step you missed, or how did I get rid of the x's? Okay, so this step, what did I do? I replaced row 1 by row 1 minus x times row 2. So row 1 was 1x x squared. Row 2 had entries 0, 1, 2x. So this is 1x x squared minus 0x 2x squared. And let's think about what happens place by place. So 1 minus 0 becomes the 1 here. X minus x becomes the 0 here. And x squared minus 2x squared becomes minus x squared. So does that make sense, Noah? Okay. And you can play the same game in the third column. The third row there is just 0, 0, 1. So that's essentially set up to make it really easy to make zeros in the entries above by taking combinations of the rows. All right, so what does it mean that we were able to get to the identity? Oh, sorry, that I wrote W. I wrote F instead of W. So thanks for catching that. Okay, what does it mean that we were able to get to the identity? What does that tell us about F? Exactly. So somebody in the chat said, this is telling us that the set of functions we have on the interval where we're working, right? We didn't really have to refer to the interval at all, has to be linearly independent. So there's no way to take a linear combination of 1 and x to build x squared. There's no way to take a linear combination of 1 and x squared to build x. There's no way to take a linear combination of x and x squared to build a constant. Okay, these are different functions, in other words, fundamentally different functions. All right, so I think I'm going to stop there for today, at least in terms of the notes. I just wanted to ask how people are coming along with the Webassign homework.
Good. I just had a question about the inverse matrix one, the first question, I think. Or was it it was the one where it was like which one is the scalar multiple of like the REF form or something like that. And
Okay.
like I couldn't figure that one out. And like I don't know. It didn't make sense to me. So if you could like go over that either like today or like next class or something, that would be great.
Yeah, we've got a couple of minutes, so I'm going to try to log into Webassign and pull that one up. Okay.
Okay.
I have an issue with Webassign where it said my free trial is over.
Okay,
Why?
so you have to pay for it.
Okay.
All right, so identity. Let's do this. All right, so let me share the screen here. Oh, shit, that's not what I wanted to do. Here it is. All right, so this is the assignment. We should see, right?
Yes.
All right, so which of the following is a scalar multiple of an identity matrix is the first question. Well, this column vector of zeros is not a square matrix, so that's certainly not going to work. This 3 by 3 matrix with all 5s is not going to work, right? You need 1s in the diagonal, zeros elsewhere. If you multiply by a scalar, every entry is still going to be exactly the same. So that can't work as an identity matrix. Okay. What about the 3 by 3 matrix with all zeros? Well, that would just be 0 times the 3 by 3 identity matrix. So that, in fact, is a scalar multiple of the identity. The next one here, we've got -1s on the diagonal, zeros everywhere off the diagonal. So that is -1 times the 3 by 3 identity. And then the next two matrices are not going to work because their entries don't follow the right pattern, right? So one's on the secondary diagonal, right? I can't have a 0 here in that upper right entry and be a multiple of the identity other than 0 times the identity. But if I had 0 times the identity, every single entry would be 0. So this guy's not going to work. And then the last one is 3 rows, 4 columns. So it doesn't have the right shape. Okay.
Okay, thank you. That helped a lot.
You're welcome. Now, we haven't actually talked about inverting, finding the inverse, but we haven't done this in great detail. But the idea is to try to, oh, no, did we do this? I think we did actually. So you can set up an augmented matrix, put the A on the left, put the 2 by 2, in this case, identity on the right. Think about going towards RREF form. At the end, you'll have the identity matrix on the left, the inverse of the matrix on the right. So I think we did this. So that's just a calculation of the type that we've talked about. And I've got a lot of questions on entering these things. Remember to use these arrows to get your matrix that you're entering into the right shape. So the right number of rows and columns before you start trying to enter your answer. 3 is the same way. Basically, you can just try to compute the inverse. If it works, you can write down the inverse. If it doesn't, say it doesn't exist. And for the fourth problem here, first you want to pull off the coefficient matrix. It's got to have entries 3, 5 in the top row, 2, 4 in the next row. So that's your matrix A. You want to find the inverse. Okay, and if you have the inverse, you can easily get to the solution. So if you have any more questions about the Webassign, remember I have office hours tomorrow morning. You can use the Ask My Teacher feature in Webassign, or you can send me an email. I'll try to answer any questions, okay?
Thank you.
You're welcome. Have a good day, everyone.
I have a quick question. Where are the videos posted?
So there are some videos posted that were made previously, and the videos from Dr. Driscoll are there. I'm having a little bit of trouble with the YouTube page set up, but I think I'm close. So the bottom line is they're not there yet. They should be there close soon.
Okay, because I'd emailed you like Friday or like sometime over the weekend because I'd missed class on Thursday. If I could get like a copy of the lecture on Thursday.
Yeah, the problem is these videos are the files are very large, so I can't really send them by email.
Okay.
So I'm sorry about that. But as soon as it's posted, everyone will know. Okay.
All right. So what section of the book was it in then? So then I can just take notes from there.
So we were talking about 1.4 and 1.5, I guess, last week.
All right. Thank you. All right. Have a good day.
Okay. Thanks. You're welcome. Bye. Assad, did you have a question? Let's see here. 3. Oops. Let's 2 next. Math. Let's do this. Done. Okay. Okay, I have to go, Asad. Please ask if you've got a question.
Oh, my bad. I was just working on a question, problem, but I don't have any questions.
All right, have a good day.
Yep, thank you.